Hello everybody, I am Buso, a researcher from Delft University of Technology. Together with my co-authors, we developed a soft robotic module for sensing and controlling contact force. And now I'm going to show you what we're talking about. Have you ever felt uncomfortable while sitting during a long car trip or after a long day at work? Well, we might have found a solution to this. We all know that soft robots are particularly suitable for direct contact with users, thanks to the soft natures of the materials they are made of. So, we thought to apply this new technology to support devices such as seats and mattresses.
All of us have different body contours and assume different postures over the day, which result in different contact pressure distribution. Studies demonstrate that it isn't possible to achieve the most comfortable pressure distribution with uniform stiffness. The image below shows that most of the pressure should be allocated in the back of the seat, where the sitting bones are, and less pressure should be in the front, close to the knees, because in that area our legs are very sensitive. Therefore, with our soft robotic module we want to first, sense the deformation of the seat. Second, actuate the module via a pneumatic system. Finally, reach the most comfortable pressure distribution. Our contribution is a stiffness tunable module with several advantages. It's low cost because it's made of cheap off-the-shelf components. It can sense deformation without the need of sensors on top of the contact surface that would interfere with the user experience otherwise. It is able to sense the contact force as well as shape. Lastly, when the module is not active, it provides passive stiffness thanks to the foam inside. We envision a seat made of a plurality of pneumatic modules that can collaborate in changing the shape and relative stiffness of the seat. Now, let's have a look at how the module is made. Here you can see our bellow-shaped actuator made of coated fabric. The inlet tube is inserted from below the module. If we look inside, there's a hollow foam cylinder. At the bottom, right at the center of the hollow cylinder, we embedded the optical sensing system. It consists of an LED, here in the middle, emitting light upwards, and 4 phototransistors are placed around it. Having the hollow foam cylinder brings 2 advantages. First, it provides some passive stiffness when the module is deflated. Also, the more regular geometry of the cylinder simplifies the relation between the shape of the actuator and the light measurements. In this way, a smaller amount of samples is required during data collection. In this study, we show that our optical sensing method achieves accurate proprioception solely through changes in light reflectivity and without the presence of a color signal. This principle has been demonstrated in a recent paper by Scharff and others, color-based proprioception of soft actuators interacting with objects. This is how it works. The light emitted by the LED is diffused inside the hollow foam cylinder and reflected by its walls. When the module is compressed with a force acting on top of its contact interface, less light is absorbed by the walls. Hence, the phototransistors detect an increment in light intensity. The illustration on the right shows a free body diagram of the contact interface. Air pressure alone is not enough to predict the force on top of the bellow. We demonstrate that the shape indicators from the optical sensors and the air pressure combined provide sufficient information to accurately predict the load. We trained our optical sensing system in a tensile testing machine and fed the data collected into a feed-forward neural network. We had 5 inputs, 4 light values and 1 pressure value, and 1 output, the contact force value. Here are the main results of our trained model. As you can see from the graph on the left, we obtained a mean square error of 4.73, and we observed that the accuracy increases at larger internal forces. The graph on the right displays an interesting effect that we noticed when we trained a support vector machine regression model. Even if it resulted with lower accuracy, in the regression plot we distinguish different lines that correspond to a different starting air pressure in the data collection. Once our model was validated, we implemented a PID control algorithm. The predicted contact force is the input for the PID, that then outputs a PWM signal to power the air pump. As you can see from the experimental setup, we were inflating the module until the target load was detected by our optical sensing system. We repeated the procedure for a target load of 20, 30, 40, and 50 Newton. The force gauge fixed on top of the actuator shows that our soft robotic module is able to correctly stop the inflation when the target is reached, with a maximum error of 2 Newton. In our paper, we showed that our soft robotic module is able to sense and control contact force. However, we are working towards further improvements, such as optimizing the manufacturing process of the module, because with coated fabric it's slow and not consistent, including a larger variety of loading conditions in data collection, training the module for height as well as load, finally applying transfer learning of the calibration model of one module to another. When a whole surface is made with a plurality of modules, for example a seat pan, comfort evaluation is needed. In this way, we can test with real subjects to discover their comfort perception and preferences. Also, we should test the precision of the overall surface and its behavior during long-term use.
Nowadays, the problem is that during and after long travels, by car, plane, train, or bus, passengers feel stiff, tired, and have discomfort. This soft robotic system is promising, as it's able to adapt itself to a specific user, and over time it will be applying changes, resulting in posture variation, making people feel fit after their travel. Check out our paper for more detailed information. Unfortunately, I cannot hear your questions right now, but we will be more than pleased to answer any of these. Please email Professor Vink at p.vink@udubs.nl. Thank you. I hope to see you in person next time.